Hello everyone and welcome to this week's Armagh Astrobytes, where we take astronomy and break it down into bite-sized chunks. We're joined today again by Professor Michael Burton, who's the Director of Armagh Observatory and Planetarium. So today we're going to talk about the daily life of a star. And to start off, I have one question for you. So we can see the outside of a star, but can we see what's happening inside of stars?
Well, that's a very interesting question, a very important question. And the short answer is no, we can't see directly what's happening inside, but we can infer by, first of all, seeing what's happening in the outside and trying to work out what's happening in the inside, but also by writing computer models, making computer models. The key thing that's happening inside a star is that they're nuclear fusion reactors, and right in the very core of the star, hydrogen is turning into helium through the process of nuclear fusion. And by the famous E=mc squared formula of Einstein, energy is being produced. It's being produced by gamma ray form, and those gamma rays work their way out to the exterior of the star, and that's what we see as visible light.
Okay, and can we see this nuclear fusion at work?
Well, we don't see the fusion at work, but what we see is the result of it. And that's essentially what's happening when we look at a star. So the gamma rays have percolated out. They're losing, degrading in form, and then converted to more and more photons, and they come out as visible light. But that visible light actually appears in different colors. And in fact, that's the most prominent thing we see when we look at different stars. We see different colors. We see red stars, we see yellowy stars like the sun, and we see blue stars. And the key is that we now understand that color tells us about how hot the surface of the star is. The surface being the photosphere where the light escapes from. Red stars are maybe about 3,000 degrees, and blue stars are maybe 10,000 or even hotter degrees. So we learn about temperature by looking at color.
So what is actually causing this? What would be the difference between the red and the blue stars?
Well, that's a very important question, a very deep question. Astronomers now understand it. In fact, it's so fundamental. This diagram I'm showing now, which is a bit technical, I will admit that, is known as the main sequence, but it's the ABC for astronomers. Let me try and explain what it is, because it's essentially, if you understand this diagram, you understand most of the life of stars like our sun. It's a plot of two things. It's actually a plot of the temperature, the surface temperature of a star versus its luminosity, how much energy is actually coming out. The original plot that actually was made here actually showed what's called color versus brightness, and was made by two astronomers called Burton and Russell in the early 20th century. We now understand that these two quantities are really the equivalent of temperature and luminosity, but because of the way they plotted color, the temperature appears to go backwards. Astronomers sometimes have these diverse units where the temperature scale is going backwards. But the key thing is, on this diagram, you see a lot of dots with numbers by them. Those numbers tell you stars and how massive those stars are, particularly the one with a 1 by it. That is our sun. It's got 1 solar mass, and there is its temperature, about 6,000 degrees, and its luminosity, 1 solar luminosity. So essentially, the temperature axis is the color, and what we find is the color is determined by the mass of the star. So the key point is that the temperature can be interpreted by how heavy the star is, how much fuel essentially the star has got in.
Okay, and how long will a star burn for? How long will it exist for?
So if that diagram was showing you the main sequence, and stars like our sun sit on that main sequence, a single spot, essentially with temperature and luminosity for a very long period of time. So I'm showing you a picture now of what our sun looks like today on the right, and what it looked like about 4.6 billion years ago, soon after it formed. And look, there's not much difference, is there? They look pretty much the same picture. The sun doesn't appear to be changing very much. Actually, it's not quite true. There are a number of things going on. The sun has now converted over that period of time about half of its nuclear fuel, half of the hydrogen in the core has gone to helium through fusion. The luminosity is increasing, not much, but every billion years or so, it's about 10% more energy. So the sun has actually got about 50% more energy coming out now than it had when it formed. It is getting slightly hotter. It's about 5,800 degrees Kelvin. compared with 5,500 when it was formed. And we're about halfway through its lifetime. We think there's about 7 billion years left, in fact. But that being said, this rise in luminosity, this rise in temperature is going to mean that at some point, probably in 1 billion or so years, it is going to get too hot for us on Earth. Essentially, a runaway greenhouse will take over because the sun's luminosity is going up. But still, that's 1 billion years off. It's still a long time we haven't got to worry about it just yet.
A problem for the future.
A problem for the future, yes.
How are all stars like our sun, and what if our sun was a bit bigger and a bit heavier? What would life be like on Earth for us?
So what I'm going to do now is talk about what life on Earth would be like if our sun was indeed not that much more massive, just 1.5 times as massive as the sun. What difference would that make to life on Earth? So essentially what's happening is the sun is actually going to be somewhat more luminous, and in fact it's going to be somewhat warmer, but other things are going to happen as well. So let's talk about that. Well, the very first thing is that the Earth is, let's assume the Earth is in exactly the same place, the same size, nothing else about the Earth itself changes. Well, because the star is more massive, the gravitational pull is greater, and so the year will be slightly shorter. The Earth will go faster. The year would be about 10 months long, in fact. So not a huge difference. The luminosity, though, the brightness of the sun will be quite a lot greater. In fact, it will be about 7 times more luminous in the sky just by this being 1.5 times more massive. Essentially, the energy being produced by the nuclear fusion reactor is nearly an order of magnitude greater. The sun would actually be slightly larger, not hugely, but it would be larger, be about 20% larger. We wouldn't be getting total eclipses of the moon if the moon was the same, because the sun would actually be too large for that. But there would be a change. But if we were looking at the sun, we would definitely notice a difference in color. And that color would be because the surface temperature of the photosphere is warmer. It would probably be about 8,000 degrees. And this would lead to the increased luminosity, the increased temperature. It would be much hotter here on Earth. It'd be probably more like Venus, but more to the point, there'd be far more UV radiation. The spectrum would be shifted somewhat to the blue end, and more UV radiation would come out. If there was life on Earth, we'd be impacted much more by UV, probably much greater increased mutation rates. However, it could most likely be that life would not have had time to evolve. The most important difference is that the more massive a star is, the faster its evolution. And the star 1.5 times as massive as the sun, rather than lasting for about 4 billion years, about 12 billion years, would probably last for about 4 billion years. In other words, we humans would not have had time to evolve on planet Earth. So we wouldn't be here to be having this discussion today.
Fortunate for us then that the sun is the size it is.
Very much so, very much so.
So is life on the sun as it exists in its kind of average state, is it boring and dull?
Well, fortunately, and in the big picture, yes, it is. The fact the sun is a stable star and is not changing very much from day to day is very important here for life on Earth. If the sun was having massive changes in its luminosity output on short time periods, that would be fatal for life on Earth. But that being said, the sun still is a seething nuclear cauldron and has intense weather going on the solar weather. And that solar weather does affect us life on Earth. It affects the solar system. And we're still learning about how the sun's weather works. So now I'm changing to our latest, greatest picture of the sun. There's a new telescope called the Inui Solar Telescope, recently commissioned in Hawaii. And this beautiful picture we're seeing here is showing these seething convection cells on its surface in higher resolution than ever seen before. Some of these cells are about the size of a state or a small country. That one in the top right-hand corner there is the size of Texas, in fact. And this, we're now starting to understand the daily weather cycle. The camera that was used to produce this image on the Inui Solar Telescope actually comes from a project that Armagh was involved with Queen's University and was built by Andor Technology in Belfast. So we're very proud of this picture here because Armagh has played a role in producing these new wonderful images of the sun so we can understand and explore the daily weather on the sun.
That's amazing. I'm so glad we were involved in that project so we can see the surface of the sun. But I do have one more question. All of this element creation, all this nuclear fusion, all this light, will it eventually come to an end?
I'm afraid it will. The sun, while it's going to last for another several billion years, it will eventually start to run out of nuclear fuel, and then it will evolve off this main sequence and the sun will die. But that's a story for next week. We'll come and talk about what happens in star death next time around.
Excellent. Okay, so if everyone wants to find out about star death, they'll have to come in and join us for Astrobytes next week. So, Michael, thank you for coming to this week's Astrobytes. It was really informative and it was great to learn more about the life of a star and also how Armagh was involved in this project as well. So thank you.
Thanks, Courtney. Great to be here. See you next week.
And thank you to everyone for joining us.